So today we're really not doing anything new. Everything that we're doing today is definitely within your current grasp of information. It's definitely something that is just different in the sense that it's combining things we haven't really combined before. So we're going to basically just do a lot of problem solving today, and specifically with precipitation reactions and with acid-base neutralization reactions. So what I want to start with are the stoichiometry problems. I need y'all to have out your calculators, be able to see the periodic table because we have lots of calcs to do. Let's read through each problem and go ahead and jot down what we're reading. Calculate the mass of silver sulfide produced. So I'm making silver sulfide. What's the formula for silver sulfide? Ag2S. When, so we're looking for the mass of this. That's the guy we're going to stoich to. Calculate the mass of silver sulfide produced when 18 grams of silver nitrate, AgNO3, we're mixing 18 grams of it, is added to excess sodium sulfide. Sodium sulfide, and that's in excess. So what's our other product? Sodium nitrate. So part of this whole thing we're doing is the need for a balanced full chemical equation. And that's going to be the first step in pretty much everything we're doing for this entire unit. You got to have a balanced equation. So I need 2 sodiums, and then I need 2 silvers, 2 nitrates, and we're balanced. All right, so this one's really easy because we're going to stoich mole bridge from here to there. So what do we start with? 18.0 grams of AgNO3. What do we want to convert grams to? Moles. So for every 1 mole of AgNO3 I have, it's 179 point something. That's what I need y'all to figure out. .179 point what? Oh, it's not. No, my finger's not an eraser anymore. All right, here it is. 169.88 grams. So my grams of silver nitrate cancel, leaving me with moles. Now I mole bridge over. What's my mole ratio? For every 2 moles on the bottom of AgNO3, I have 1 mole of Ag2S. And then for every 1 mole, I need the molar mass. And to 3 sig figs, do 2 decimal places on the molar mass, and our final answer should be 3 sig figs. .247.8 what? 88? 80 grams of Ag2S. So my moles cancel. So to 3 sig figs, how many grams are produced? 13.1. That sounds just about right. 13.1 grams. So this problem, no different than what you already learned to do, except you have to predict the rest of the products and balance it. That's literally the only difference. It's a pretty straightforward little problem. Let's look at this next one. What mass of iron 3 hydroxide? This lighting is going to give me a seizure, this blinky thing. Yeah, I got to turn this in. They need to do something. What mass of iron 3 hydroxide is produced? So we're producing FeOH3, and we're looking for mass. When iron 3 nitrate is mixed with potassium hydroxide. So iron 3 nitrate is mixed with potassium hydroxide. And they give us a lot of information about that stuff. We know we have 35 mils of 0.250 molar iron 3 hydroxide mixed with 55.0 mils of 0.180 molar potassium hydroxide. All right, so what do we think? We're going to have to stoich mole bridge at some point, but what do we have to do first? Convert to moles. What's ultimately what we need to figure out? The limiting reactant, right, because I don't know which is limiting and which is in excess. I've got information about both of these reactants, so I need to figure out limiting reactant. And I heard people say convert to moles. That is correct. To do limiting reactant, we have to get both of these to the mole, to the information to moles. That's super important. So I'm going to take, how do I get moles from liters and molarity? Molarity is equal to what? Moles per, and what's 35 mils in liters? 0.035. So 0.035 times 0.250, that's going to give me moles, which is how many moles? 8 what? 7 what? All right, thank you. 0.00875 moles of this guy. And how many moles of KOH? It's going to be 0.180 times 0.055. 0.000990. 0.00990 moles. All right, and this is not a one-to-one. Oh, what did we forget to do? See, I'm glad we did this. We messed up because I need a balanced overall equation, and if those of you saw it and didn't stop me, shame on you. You need to tell me these things. All right, what is our other product going to be? Potassium nitrate, and we need 3 nitrates, and then we need 3 potassiums, and that makes our hydroxides balanced. So we needed this because we need to know the mole ratio between these two to figure out limiting reagent. So this is to 1, and this is 3. I need 3 of these for every 1 of these. Which one's going to lead to a smaller number? KOH. This divided by is like 0.003 something, right? Ish. Who cares? It's going to be smaller than 0.087. So that makes this guy the limiting reagent, and this guy is in excess. So we're going to do stoichiometry from here now to here. Again, not a problem you're not capable of doing. It's just giving you information all in one problem that you haven't seen put together before. So I'm just going to take away some of my work. I don't want to start again with the mils and stuff. I figured out moles here, 0.00990 moles of KOH. How do I stoich over? Mole bridge. For every 3 moles of KOH, I have 1 mole of the product I'm looking for, FeOH3. And then to get to grams, for every 1 mole of FeOH3, I have 106.88 grams of Fe. Can I get a second on that molar mass?
I got 106.88.
Okay, cool. All right, so to 3 sig figs, what is the number of grams we produced? .350? 0.353 grams of FeOH3. Yay, looks good. Okay, questions on that? All right, let's take a look at the next problem. The next problem says, from the previous problem, calculate the molarity of nitrate ions in the solution after the reaction is complete. Okay, so I'm just going to go back to the previous page just so we can actually see the data. So we're looking for nitrate. This is number, what number is it? 4? 11. Oh, 4. Okay. 11. So we want to know the concentration of nitrate ions. What can you tell me about nitrates? They're always soluble, right? So whatever nitrates we put in here at this point, do we agree there's going to be the same number of moles of nitrates here as here? Yeah, A, it's a balanced equation. B, they're going to be soluble from the jump, these guys. So what I need to do, using the molarity, we know that's the molarity of the whole thing, right? Okay. I need to figure out, well, how many moles of nitrate does that represent? So I have got I know how many moles. They were right here, right? 0.00875 moles of FeNO3. I've got to start with the mole at the mole level. Does everyone understand what I'm doing there? Tell me that number again, 0.00875. Just needed more room. Now, if I want to get just the moles of the nitrate ion, I can do it right here. For every 1 mole of FeNO3, how many moles of nitrate do I have? 3 moles of just NO3. Now, to get to molarity, I need a volume, right? This is the part that's new for you. Think about it. Am I going to use 35 mils? What am I going to do? Okay, ladder. Victoria, you're right. No, I thought you said something else. No, but maybe it was you. Yeah. Yeah, you add the 35 and 55 together because, yeah, this is how many moles of nitrate that we have in that dimensional analysis that were in already 35 mils. But what did we do to it when we mixed? We diluted it, right? So we need to divide then by 90 mils, right? For this is of the solution. So this is 90 mils total that we're going to divide by. So that's 0.09 liters. And that will give us moles of nitrate per liter of new solution. And so what is our new nitrate concentration? 0.292. Can I get a second on that? Good. Oh, horrible smartboard making flashes. I wonder if the video, I bet you the video is not flashing. Well, it wouldn't be because it's the smartboard that's flashing, not the computer. Okay. Do we understand that? So finding concentrations of ions is pretty common, right? One thing just to note, when you get to your homework, there's homework problems where you're adding, let's say, silver nitrate plus sodium chloride gives you silver chloride plus sodium nitrate. And they're going to ask you questions like, they'll give you, you know, the molarity in mils here. They'll give you molarity and mils here. And they'll say, like, okay, what ion is left floating around? And a lot of people will say, oh, the only ions floating around are the Na plus and the NO3 minus. Is that necessarily true? What else could be floating around and why? Yes, Amelia. Right. Looky over here. What if we had silver nitrate in excess? Did all the Ag plus become AgCl if this is in excess? No. So if this is in excess, we'd have Ag plus also floating around, in addition to over there. If this is in excess, what will we have also floating around? Cl minus, if this were in excess. So when you're looking at ions at the end of a reaction, your first step, you always got to figure out, sometimes they give it to you perfect where neither's in excess. They'll give you exact moles of the same of each, but usually not. One of these will usually be in excess. And if it is, you've got that ion in addition to the product ions floating around. Okay? So keep that in mind when you're doing tonight's homework, because that was a question people were asking me about after lecture last period. Okay? All right, so now we're going to move on to acid-base reactions and titrations. Monday, you guys are going to do your first pH acid-base titration, where you're going to take an acid of unknown concentration and titrate a base of known concentration into it to get to the equivalence point, which we'll talk about more specifically in a bit. And then from there, you're going to figure out what is the concentration. So I'm basically giving you an acid and say, figure out its concentration. So in a problem like this, yeah, you know it's a titration because it says titration up top. But if you didn't know that and it didn't say that, how would you know this is a titration reaction? It says calculate the molarity. First off, finding the molarity of an acid or base is usually the product of a titration, okay? In a 20 ml sample, if a 20 ml sample of this acid is neutralized by 18.50 mils of 0.750 molar sodium hydroxide. So the fact that it is neutralized by a certain amount of a known concentration of a substance, that's normally set up in a titration format. You don't need to know anything about a titration to do this, but I'm trying to broaden your thought process because Monday we're actually going to do something like this. And so in this case, the acid sample is in the beaker. We've got 20.0 mils of this H2SO4. And I know that because it says it's neutralized by. The thing then neutralizing it is in the burette. And so we have a burette. And pre-AP you did this with burettes last year with the phenolphthalein, remember? Regular, you did it too, but you had syringes with little turn screws on it, little burette tips on it. So it is being neutralized by 18.50 mils of 0.750 molar NaOH. So that's what the titration setup is. So whoever did this titration, they didn't know that 18.5 mils until they did the titration. Maybe they had phenolphthalein in there, maybe they had a pH probe, but something made them stop the titration at 18.5. It's like those pipettes we used. This is 0 mils, this is 50 mils. So this is measuring the addition, mil by mil, of what we call our titrant. We're adding that to the thing we're titrating, the titrant. So something indicated for them to stop, whether it turned pink from phenolphthalein, whether or not the graph, the pH shot up at the equivalence point, something made them figure out, hey, it took 18.5 mils to neutralize this guy. So now the question is, what is this guy's molarity? So nothing harder, nothing new. What's the first thing we always want to do when we're doing this kind of thing? What? Yeah, we need a balanced equation. So adding NaOH to H2SO4. Classify that. That's a what plus a what? More specifically, strong acid plus a strong base, right? So that makes a water and salt. So let's go ahead and write our products. And you can see that in the double replacement reaction. You don't even need to know that, but I want you to start knowing things. All right, so to balance this, we need 2 sodiums, which gives us 2 hydroxides, and now we are balanced. Okay, so I'm just going to write, there's some general steps you take anytime you're doing an acid-base titration, neutralization. It's, again, you can do it just knowing what you know, but I want you to start thinking through steps. Your first step, whenever you've got something, this is what I call the known, because we know the concentration, we know the volume. You find moles of known is your first step. You're always going to know enough about something to find the moles of it, and that's your known. Find the moles of known. And then step 2 is to use stoichiometry to find moles of unknown. What's our unknown in this problem? The sulfuric acid. And this is always through stoichiometry, through mole ratio. Okay? And then the third step is then at that point to find what you're looking for. Whether that be continuing dimensional analysis from the stoichiometry, it could be whether or not it's a totally separate step, it's going to depend. You can find what you're looking for after you get those moles of the unknown. All right? So, recapping what information. We know a lot about this guy. We know we needed 18.5 mils of it at a 0.750 molar. And then this one, all we know is the sample in the beaker was 20 mils. So we need to first find the moles of what we know. What do we know the moles of? What's the known? Sodium hydroxide, correct. So 0.750 moles per liter, 0.0185 liters. How many moles of NaOH do I have? Give me 3 sig figs. 0.01 what? 39 moles of NaOH. Can you get a second on that value? All right. So I know moles of NaOH now. Now I'm supposed to go from moles of known to the moles of the unknown with stoichiometry. I'm in a mole bridge, which you already know how to do. So how do I do that? For every, what goes on the bottom? 2 moles of NaOH, I have what? 1 mole of H2SO4. Okay? So that gives me moles of H2SO4. Now, I could stop here and write that down, but what am I really looking for? What was the question? Calculate the molarity of sulfuric acid. If I know moles of sulfuric acid, what do I have to put down here? The only thing? The liters. So what's the 20 liters? 20 mils in liters? 0.020 liters. Now, I hate to say this because I don't want to confuse you, but students will sometimes want to add these two up, okay? You don't do it. You'd only do it if they're asking for what's the molarity in the beaker after the titration, because in the beaker after the titration, you did have an increased volume. The question wants to know the original molarity of these 20 mils. So it's just of the 20 mils. You don't do any crazy addition. So what is my molarity to 3 sig figs of this guy? 0.348 moles per liter. Okay? How come we used 18 mils of the base and it had a molarity of 0.750, but we used pretty close to 18 mils of the acid. We used 20 mils of acid, and its molarity is so low. What's making that happen? Naira? Yeah, it's a 2-to-1 ratio. So for every 2 acids, for every 1 acid, we need 2 bases. So that has to be almost double in concentration, which makes sense based on the numbers. Okay? All right. Let's do another one. Moles of known, moles of unknown, then you find what you're looking for. So how many grams of barium hydroxide are contained in a 25 ml solution? This time our base is in here, and it's 25.0 mils of barium hydroxide. But what are we looking for? Grams. That's our question. How many grams of this barium hydroxide? And again, you don't have to draw up the titrant and the whole burette thing. I'm doing it to get you used to titrations. In the burette, we have HCl. Somebody did the experiment and found out it took 16.52 mils of this 0.850 molar stuff to reach the equivalence point. So we're going to first write a balanced equation. So HCl being added to barium hydroxide. What's our final product? Acid and a base always makes water, Na. What salt are we making? Barium chloride. So we need 2 Cl's, and we need 2 OH's and 2 H's. So that'll work. All right. So the first step is to find moles of the known. What's our known? This HCl is. So how do I find moles of that? Molarity is equal to moles over liters, right? Wait, I have liters. Moles over 0.01652 liters. So how many moles of HCl do I have? 3 sig figs. Oh, yeah, 3 sig figs. .0140 moles of HCl. Now what do? I have to find moles of what? I have moles as known. I got to do moles of unknown. How? Stoichiometry. So for every 2 moles of HCl, I have 1 mole of barium hydroxide. Here's the beauty about this problem. We can continue. We found moles now. That was step 2. Step 3, we can actually continue on, find what we're looking for. What are we looking for in the problem? The grams. So how do I do that? 1 mole of BaOH2 gives us, we need molar mass, right? Is anybody bothered by the fact that we're not using this 25 mils? It's a bit weird, right? But you don't need it, and that happens on the AP all the time. What would they have to ask for you to be required to use that? Yeah, molarity. If they went and asked for molarity, then you would have taken the moles of BOH and divide by the 0.025 liters. But that's not what they're asking. They want to know grams. We don't need the 25 mils. It didn't matter if we added 1,000 mils to that little beaker. The grams would be totally the same, regardless. Okay? The concentration would change, but the grams would be the same. So what is the molar mass of barium hydroxide? 171.35 grams of barium hydroxide per mole of barium hydroxide. So what's our final grams of barium hydroxide to 3 sig figs? We got 1.20. Is that what y'all got? Okay. So again, nothing beyond the scope of what you're capable of doing, just presented to you in a slightly different way. And again, you don't have to do this part. I'm trying to get you used to the concept because you're going to do the titrations, but you're not going to be given this value. Your job will be to find out how much base or acid is required to neutralize what's in the beaker. And then do the calc like we already know how to do the calc. Okay? All right, this last problem is kind of a sexy little, cool little problem that's really easy, and there's not actually a lot of work to do. And they want to know, hey, if we're mixing 25 mils of 0.65 molar HBr, so we're mixing 25.0 mils of 0.625 molar HBr with sodium hydroxide of 42.0 mils at a 0.352 molar, will the resulting solution be acidic or basic? What are our products of this solution? Water and salt. This is a neutralization reaction. Strong acid, strong base means that we really shouldn't have acidic or basic. We should technically, since this is strong, have a pH of 7 after this is done. But it won't be, because what do we need to figure out? Limiting reactant. So if it's limiting, is that what's going to make it acid or base? What makes it acidic or basic? What's in excess? So we figure out the limiting reactant. Whatever is in excess, that's going to make the solution acidic or basic. So this is a 1-to-1 ratio. So all we need to do is figure out which one of these has more moles. So molarity is equal to moles over 0.025 liters. So 0.025 times 0.625 is what? .025 times 0.625. I'm sorry, I can't hear anybody. 0.0156. Does everyone agree with that? All right, so that's moles of the acid. Let's check out moles of the base. We have 0.352 molar, and that's equal to moles over 0.042 liters. Are y'all getting comfortable with me switching to liters really quick? Okay, you got to get used to that. What do we get for moles? So Which one's going to run out? The limiting reagent, this one is less moles, right? The limiting reagent is going to run out. This one is in excess. So is our solution acidic or basic? Acidic, because after it's all said and done, we still have H pluses from the HBr floating around making it acidic. That's pretty sexy, isn't it? Oh well, I guess we all have different definitions of sexy. So really quick, I want to talk about the lab. The lab is due tomorrow. I don't want you freaking out. If your percent copper doesn't match up exactly with one of the bullets, that's cool, because we didn't pick bullets that we knew were on the table. We just bought random bullets, like in bulk from Etsy. You can buy bullets on bullet casings on Etsy. Who knew? Because I got scared going to the gun range. I did it once. I'm never doing that again. Too many toothless, scary men calling me pretty lady. I didn't like it. It's just not my scene. Nothing's wrong with it. It's just not my scene. So anyway, point being, if you're within about 5%, pick that bullet. It's probably that bullet, okay, that bullet casing. If you're way off the bullet casing of any kind, if it's too low, I got some people getting like 20% or whatever, and it didn't, then just in number 4 say, hey, I got 20%. It doesn't really match with any of the bullets. You think I'm grading you on whether your bullet matches? No. You guys need to get over the grade thing. My concern is, do you know how to do those calculations appropriately? And if you happen to get over 100%, we have some magical folks here that specifically in this class, and who remain nameless, no, they're fine. It was these two. Yeah, Berkeley and Ruhi, good job. Like 120-something% copper. They produced copper out of nowhere. I went over the calcs. The calcs were fine. There's nothing I can do about that if your calcs are correct. So if you're getting crazy numbers, I would hope you have already come and talked to me about it, and I would have given you the thumbs up to go with it or shown you your mistake. So if you got a crazy number, you better make darn sure it's correct. And just FYI, I won't be here tomorrow morning. I won't be here in class tomorrow. I'll be here in the afternoon, but it's due in class. So go see Miss Rozier in the morning. She will be here if you're questioning your calcs. But not a fan of that happening on the day the lab's due. You had today to do that, and you still have this afternoon to come see me and work those problems. Yes? No. Corrections cannot be done in Miss Rozier's room. And I'm only gone literally half day tomorrow. I've been here every day. I will be here every day. It's literally half day tomorrow. I'll be gone. All right. That's it.